Hi guys, let's get started. 7 p.m. All right. Today we are doing at this hour we do the review of lecture 6, higher order function. I took some of my materials from here. Uh, Actually, inert functions, it's not quite higher order function, but in there it involves higher order function also. Okay, so I will, you got a chance, you should read it. They are much more detailed, explaining more clearly than what I'm going to do. Okay. All right. In Python, function are so-called a first-class object. All right, means first-class citizen. It's treated like any other things like numbers, so strings, lists, tuples, modules, and so on. It can dynamically create or destroy them, store them in data structures, pass them as argument to the other function, and use them as return values and so forth. Okay, so higher order functions actually this it's not common in other programming languages like those C, C++. Generally, it doesn't support it. Java also. Uh, but one thing to note is that by supporting higher order function doesn't mean that Python is more powerful than all the other languages. As always, languages are created to some extent equally, or they may be created for certain domain that is easier to use. But after all, the computational power, meaning that the expressiveness or the way that you can solve problems, are more or less, or I should say that they are all equal in the sense that if there are certain things that cannot be done computationally, Python, other languages cannot do, and Python surely also cannot do. Okay, so they are all equal in that sense. All right. All right. It's just that by allowing higher order functions, just like many other libraries that providing the libraries to you, allows you to do things maybe more conveniently. All right. But it doesn't mean more powerfully. All right. So it's only for convenience. That is to say that if Python can do it, other languages can do it maybe in a more roundabout way. So it may not be direct, but still, it's doable. Okay, but because you can do higher order function, it also means that things can get a little bit more complicated. Okay. But it comes with a cost. Everything that you have, the more that it's provided, the more it's more effort or for learning and for understanding some of this peculiarity in the language. All right. So uh, that particular this particular web page, you should take a look why it allows. I pretty much took it from there. So there are a few things that I'm going to take this opportunity to show you how things can be done. And the first one is encapsulation. The word encapsulation means that you are uh, like you take medicines, the medicines that those very bitter medicines, you encapsulate it into capsule and you swallow it just in one go without having to know what is inside. And you get away with all the bitterness also. So in Python, with the higher order function or so-called the inert functions, all right, function that define within a function, allows you to put things into capsule. Here's an example I want to show you. So this example is in the lecture notes, change coin. So I want to change coin. I want to change 30 cents with coin of 1, 5 cent, 1 cent, 5 cent, 10 cent, 20 cent, 50 cent. Of course, you only have 30 cents, so 50 cents is useless. But anyway, I use 30 cents because it's easier for us to check. All right. So I want to count number of ways to change 30 cents. So here's the program that you have it in your lecture. All right. So uh, if the amount, so there are two parameters here, amount and kind of coins. So if the amount is zero, that means that you have you need to change only zero the zero money. So of course it's one way. Okay. But if you need to change negative money or the kind of coins you have is zero, then you should be zero. Okay. So, and otherwise you will have, you can change money in two ways. First, you keep the amount, right? And you use one less coins. Okay. Or you take that amount, subtract away one amount from the coin and keep using the same number of coins. Okay. And there's no overcounting and no undercounting in the sense that this undercounted the part that have to use the particular coin, the last one. But it's complemented with that the you use the coin already, subtract it away from the amount, and you keep the number of coins. So the sum of these two give you the total numbers. So the denominations of coins are 1 cent, 5 cent, 10 cent, 20 cent, 50 cent. So if you want a particular kind of coins, you return that coins of that kind minus one. The index is minus one because it's index zero, index one, two, three, and four. Okay. So if you run this, we get 20 ways. Okay. So this is the answer. So what do I mean by encapsulation? So for example, what you're seeing here is that this first denomination, nobody need to know, all right, except that this program is running. All right. And coin change, count change, which is the function you're calling, and you call this amount only, and you need to invoke the function CC, which is this guy, with five kind of coins because there are five here. Okay. So actually, nothing about CC need to be known outside. Nothing about first denomination need to be known outside. So I can encapsulate these two guys within count change. All right. So that is what my next version will do. All right. So this is what I will do. I will simply hide CC inside here. I hide first denomination inside here. When I say count change, I go into count change with the amount and I return this. So 5 is hidden as well. All right. And this code, so let me comment out this one. You again get the same answer. All right. But the difference now is that if you try to call first denomination 3, for example, hey, did I do something wrong? Oh, because I had it here. So I should comment out all this chunk. Okay, let me try again. Okay, the answer is 20. First denomination, if I do that, I'll get error because function is now encapsulated within count change. All right, so in this way, the code in a way is cleaner. Instead of three functions, now you have one function with two inert functions. All right, so that it's what it means by encapsulation. And I wanted to take this opportunity to also show you carrying baggage. I mentioned this some time ago. In recursion, what you do here, you needed two things. Number one, the recursion has to be getting you smaller answers. Sorry, here, the smaller prompt. And then you also need to get base cases. These are the two base cases. Okay, so there is a third thing, so which is called carrying the baggage. I wanted to show you. It's just an extension of encapsulation, but not necessarily mean that. Okay, so we had terminating condition, which is the base cases, and smaller prompts, which are the two smaller prompts. Now I want to show you carry baggage. Now, you know that there are 20 ways to change 30 cent. But suppose you want to know exactly what are the 30 ways, what do they look like, then you would have to list them out. Okay? Listing them out, it's not that difficult, actually. So let me just amend this code, this version 2, to give you exactly that answer. All right. So first, no change to this code. Count change 30, it will comes in as 30. Now, what I needed to do is that I needed to, my original baggage is empty. Okay. So which means that my count change now has a third parameters here. Okay. This third parameter is my baggage. Okay. And this baggage is going to carry with me into, for example, when I know that I don't use I don't change it, I just maintain it. That means that I didn't change my baggage. All right, so actually I can just put my baggage here, the same. Whatever comes in, it goes into the next level. But I also know that when I'm here, amount equal to 0, at this moment, I actually don't use any more coins. So let me just print out the answer here. Okay, whatever baggage I had at that moment. And when I reach this statement, actually I have no ways to change, so there's no baggage. The baggage is useless. Whatever I have collected, my baggage, it's not going to be useful to me. Now, the only last thing that I needed to do is this guy, amount minus this and kind of coin. What is my baggage now? My baggage now is whatever I had before together with what I have used to change. So it looks like this. Instead of typing, I just cut and paste. Is my baggage. Put a space there to separate things. And this is what I use to change. And I need to do a continuation. And that's all I have to do. And I got my baggage carry deeper and deeper and give me the explicit 20 ways of changing my coins. Let me run it and see how. You see, to change 30 cent, you can use 31 cent coins, or you can use 25 of them, okay, plus a 5 cent coin, or you can use a 20 cent and a 10 cent, okay. All these added up, there are 20 ways. 2, 4, 6, 8, 10, 2, 4, 6, 8, 10. All right. So carrying baggage into the recursion is something that kind of interesting. You should take note of it. It can be helpful. Basically, along the way, finding of the solutions, you collect the partial answers. And with the partial answer until the end, you just print out the answer. That's how carrying baggage it's helping us to explicitly list out all the answers in this way. Okay, any question? Yeah, okay. All right, there are many more examples that you should try it out. Uh, Other than just counting a number, this is giving you a number, you can actually explicitly list out how do you arrive at this number. Here, you see, they are all here. The way, 6 5 cent coins to change the 30 cent, also correct. Everything in here is correct. As far as your number is correct. So what I did was simply taking the original code, added in a new parameter baggage to be collected along the way into the system. So talking about that, you could try it out with Tower Hanoi, all right, which is another example, and you can add this baggage to show you how the Tower Hanoi can achieve the goal of moving from one pile to another pile. Okay. So there is encapsulations, and I took the opportunity to show you more than that. What is next? Let's see. The next thing is about reuse of code. I say this very often. That is, we try to write as little code as we needed to, so that we don't have to test those new codes. Basically, we are reusing codes. Uh, here is uh, Here it's the example of define sum to be like that and define product to be like that. In the case of multiplying a chain of numbers together, the default is 1, then you multiply the thing. To sum up a chain of numbers, the default is 0, and you just add it to the recursion part. Same here, multiply with the recursive part. All right. So these two programs or these two codes, definition of sum and definition of product, actually look so similar. And indeed, this can be unified in a way into one code, as you are going to see later. I think something like this. All right. Something like this. Then you can use the same template, the code to actually, I think it's in the next slide. Okay, this one is not here, but you can try, you can see it out. You just have to abstract out this 0 versus the 1, and then the plus versus the multiply, and put it into the parameter. Then you would have one program that will serve two purposes. You can serve it as a sum, or you can serve it as a product. Okay, so the way that Python allowed you to use higher order function as a first class object to allow you to then abstract things out into a code that you need to test, only just that code, and you can apply it many, many times. All right, we're going to see that in recitation number 3 afterward also. Okay. The next one is another interesting thing. All right, this part of the discussion, or this part of the material, it's kind of different from other languages that you may have known, in the sense that the Python support the higher order function, being a function as a first class object. And so there are certain things, if you are familiar with traditional languages, you may have to learn this part in a different way. You have to learn this part. I want to refer back to repeat pattern lecture 6, slide 40. I think this is one of the things that I have shown you before. Repeat pattern, which was the code that I draw repeat pattern, and this was the function. And you could write it in many different ways, or another different ways, as what we had it in the discussion forum. Here, this is another slide as homework, that you take these three things as an input to give you a picture. You could have broken it down into, instead of 3 parameters, you take 2 parameters, the two of them, and give you another function, right? Because a function, it's a first class object. You can output it also. You can take it as input. You can also output it as you can take it as input. You can also output it as result. So you can do that. And then this function is here that you can take picture and give you picture. So instead of passing you 3 parameters in one go to get a picture, you can first define this function, and this function can be named in such a way that it's convenient to be remembered. Okay, so let's see how I can do this, and then we can take the pictures and then just output it. So here is what I use. Okay, let me comment out all the rest first. Okay, we're just looking at this guy. Yes. All right, this is the original code with 3 parameters. All right, you get this. Okay. So now I want to get this and with two separate functions. So how do I do that? Okay, so let me just comment out this. So I want to follow this picture, okay, to give me a new function called npad. Then the npad is supposed to take that another picture as. So I should take this. I will try to take this, and because this is going to take two parameters, so this is out. The third bit is out. And I want to, because this guy is going to output a function, so I have to define an init function. The init function is now npad, and this npad is to take picture. Okay, because this is an init function, so this has to be indented. All right, and then I have to then return npad. Okay, so but you know that this is a repetition. Okay, so by doing this, I don't want to go out to repeat this guy. Instead, I need to define yet another helper function, and in this time, it's also the npad. Okay, and this has to be indented, and this guy it's then return helper npad. Okay, that's not the end. Let's check. So this is the recursion part, and this recursion part is to call helper and instead of repeat pattern. All right, repeat pattern is the outside guy, so this is a helper. And this is n minus one, go in there, pad. There shouldn't be another picture here. Okay, so and let me check. Yeah, it looks correct. Now, a few comments about this. This n and this n are not related. As you will see, this is so-called a scoping because this is an n, this is another n. So it may look like they are the same, but actually this n and this n are the same, but not this guy. So if I claim that, maybe I should change it to m to make it, and this is m, and this is m minus 1 to make this clear. And also, this pad and this pad, actually, they are not related because these are both parameters in the function already. So, but this pad and this pad are the same. Okay. So, if I want to prove that, I will have to use this changes to pad and changes to pad. Changes to pad just to confuse ourselves, but yet to prove the point that indeed this guy and this guy are not relevant. Okay, now I've done my change from this function to give me this function. Okay, now you see that this is a function because this function actually take a parameter, but there is no parameter stated here. Okay, so it actually output this whole function. All right, so how do I use it? I will use it like that. All right. Now I give it a name. Make cross 4 times with, because with is because I'm going to pass in a picture. And the repeat pattern for make cross, which is the same as repeat pattern for make cross, except that this parameter nova bb is not there. Now I want to show the with nova bb, then I will just do this. Okay. All right, let's try. Hopefully I'm not wrong. Okay. Okay. So I've succeeded in making a function of 3 parameters into a function of 2 to return yet another function that looks like this. And this guy subsequently just need to take one picture to output it. So, and I take the advantage of naming it something which more meaningful rather than this repeat pattern for make cross nova bb, which may not make much sense until you check the code. But here, make cross 4 times with. This is explicit. All right, we can also try this with other example. All right, part. It comes to my screen. All right, you see. Okay. So this is how I can actually uh, create a name for my function that more meaningfully. Okay, so this is part C. It's closure of environment, meaning that what you saw just now, this n and this pad, they are used in here, this n and this pad. These are the environmental thing that which I pass in with for and make cross. They are registered in here as for and make cross. All right, and the rest of the function also know about them. But this, even if I change this to n, just to prove the point, and there's no difference to the answer. That is to tell you that the scoping, which is another important part of the, I can change this back to peg. To, that's all, yeah. Okay, it's still the same answer. Okay, so that it's closure of things that the environmental environment like for and make cross are enclosed within it, and we can have. All right, so this is actually the next point. It actually make the name that help us to. Okay, so ease of reference now. I have created another abstraction and I am naming the get me something which I can understand. Here's another example on power. I can show you. All right, power base exponential. Return the base raised to the power. So when you write this power 2, 3, is it 2 to the power 3 or 3 to the power 2? You have to go and check it to see it. All right, so let's try to run it. Can we just comment out this guy? Oh, this is actually 2 to the power 3. Okay, this is actually this one, not 3 to the power 2. 3 to the power 2 is 9. So this is 2 to the power 3. It's 8. It's 9. All right, so but this is not so easy to read, all right, in some way. So how about this one? Looks like this. All right, so generate power exponent, define power base, return base to the power of exponent. So raise to the power of 2, 4, in this case, generate power 2. So now it become very clear. All right, raise to the power of 2 for 4, which means 4 square, which is 16. All right, 16. Okay. So now things will look more explicit rather than power 2, 3. And you always have to remember, oh, it's 2 to the power of 3 or 3 to the power of 2. But this giving you a bigger, longer name, but it make explicit what things are. So if you want power of 3, uh, you want to raise something to the power of 3, then you write in that way. Again, you do the same. So this should give you 4 to the power of 3 will give you 64. All right, 16 and 64. Okay. Yeah. Okay, so that it's the another example with power of making things more explicit. Now, as I said, there's no free lunch, so you have to learn about some of the stuff that I said earlier. Like, it may take a while to realize that the what I said just now about this guy is actually this guy, but not this guy. Okay, so these are the scoping that you have to know. So here is what I have. All right, scoping of parameter, and you will see that also in recitation shortly. You define a function 1, x, and define init function 1, 1, x. This x and this x is not the same anymore. All right, x is the x in function 1, 1, just like here. N is the n within helper, nothing to do with the n outside of helper. Okay, so this is one thing you have to take note. The second thing is that there's this thing called forgiveness attitude. And we will also see this. If a value, not variable, is variable, it's not on the right-hand side, it can be obtained from the global. Otherwise, one need to declare it's a global to be on the right-hand side to use the variable. See in recitation shortly, and we'll get to that. This is the forgiveness attitude. Basically, if you don't define a particular variable, but it appears inside a function, then that variable could be taken as from outside. Is quite forgiving, okay, in that sense. But if you have assigned new values to that variable, then you cannot be forgiven because that variable is a local now, okay, because you changed the values. I will see that specific example shortly. The second thing you need to watch out when you're dealing with the higher order function, it's something like this use of lambda function. So maybe I have time, I will show you now. Okay. All right. Lambda function is something which unusual in the sense that it's a function without a name. Okay. It's a shorthand to write function without giving it a name. All right. We needed this because of higher order function very often. As you will see, we pass function around, but we cannot write in this manner, define blah, blah, blah. We have to use something like this. So you define a function with any name, x comma y, return x plus y. This is the same as lambda x comma y, which are the inputs, and you add them to be the result. Notice there's no name to this function, number one. Number two, you see there's no return statement. Okay, don't write a return statement. Something like this with a return is wrong. Okay, so this is the wrong statement. When you write this, Python surely complain. Okay, so this is one thing's different in Lambda. The second thing, right, it's that the Lambda doesn't allow you to write if statement as before. You're writing if colon return this else colon this. This is not the right format for Lambda because it's a shorthand. You have to write it in this manner. If without colon, if this is true, you are using this as the answer. If this is false with the else statement, you are using this as the answer. There's no colon, no return, and so on. This whole thing is the same as my, you give it a name if you want to, xy, because if x larger or equal to y, you return x. Otherwise, you return y, meaning that you're comparing x with y. So if x is larger than y, you are returning x. Otherwise, you're returning y. That is you to find the largest of the two numbers. Okay, so this statement is the same as this. All right, so this is the lambda function. Take note that it doesn't have return. It doesn't have the normal if statements. The if statement is written in uh, the true part, then the true condition, and then the false part, with the return. You can cascade this thing with this y could be substituted with another lambda if you want to. Okay, so we will see this again later on. Okay, so this is something you have to learn about higher order function and do more practices of that. Here's another example, semantic versus syntactic. Okay, so let me get. Okay, uh, hold on. Let me check that I don't show you the answer first. Okay. All right, here. This is taken from a midterm in 2020 during COVID time. Right, here are two functions. Define blur x, return lambda x, x raised to the power of 2. Define king, return lambda x, x plus 2. Right. So the question is 2 marks, which is very small little marks, very little marks, because the whole paper has 32 marks. What is the answer of this? Let's try. Ethan, what do you think this is?
Let me see.
Yeah, we have time to see. You have done the exercise or the mission with the tries. This is in that kind of spirit, but much easier. Okay, it's
Mm,
just a trick question.
is it 100?
Oh, yeah, a number of you get 100. Interesting. No, the answer is not 100. The answer is 16. You look carefully. Blur x is return a function.
Mm,
This x and this x, any relationship?
no.
No. Okay, then you got it. There's no relationship. I don't care. I don't care what is passed into x. Okay. Okay. Ultimately, it's going to return me this function. So for this blur, whatever you give me, king, whatever nonsense, it's not going to care. All right. This
Mm,
blur is going to take this king to become lambda x star star 2, which
oh,
apply to 4, give you 16. All right. Next. What about king? Ethan, let's try this one.
is it 6?
Yes, it's correct. All right, now you learn it. Uh, whatever king, it's this x has nothing to do with this x. All right, as what we did just now. This n has nothing to do with this n. Okay, and therefore, whatever blah 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 you give me is useless. I'm going to give you just the lambda. Okay. Actually, if you substitute blur into blur, you get nothing. You just get lambda this. You get this, you substitute into blur, again you get this. And this go into king or still get this, still plus 4, give you 6. What about this one, Ethan? This is another straightforward now.
It should be 16 also, right?
Yes. What is the next one?
Uh, 6.
6. Yes. Okay. That's why it's only 2 marks, because once you see the trap, you get whatever needed. All right.
Okay.
So thank you.
Thank
So
you.
welcome. All right, so this is what happened. Okay, I'm pretty much done with the discussion. Maybe I want to just make a point here in case afterward we quite long. So let me just steal the time from here. All right, the next recitation, it's going to talk about sum and fold and uh, the some of this stuff you're seeing at this level of the education, that is, we are now at the tertiary education. We actually create things ourselves. If you see sum, actually Python has a thing called sum, but we are not to be confused with that sum. Yeah, it's a function. All right, let me try. See, sum can sum something. No, sum. Oh, it looks like this. Term A next B. Oh, actually, this is misleading. I already have my sum down here. Yeah, I have it here. Okay, so this is not the system sum. I have to start a shell. Restart shell. Let me see sum. Yeah, this is a built-in function. I don't think there's a full. Yeah, no full. In any case, you should note that sum or whatever we give you at this level of education, you have to take it on what we give you. Ignore whatever is in the systems. Okay, unless whatever we give you without details, then it means in the system. Okay, but in this case, in recitation 3, actually we have this sum defined by us, yet there's another sum in Python. All right, I don't know how this works. Let's check it out. Oh, it looks like this, sum. So which is what correct? Sum, zero, yes. Sum. Okay, so this is a sum of a tuple. This is a sum of a list, and it works. Okay, so we will just take whatever we give you and we work on that. All right, I'm pretty much done with the review for now, and uh, we come back at 8 o'clock if you don't have a questions. Any question? I actually pull out the midterm. Yeah, it was here. The blur and the king. The answer is 16.6, 16.6. I also pull out the various this is another sum. All right. So this sum and that sum are quite different. This one only 3 terms. This guy has 4 terms. Okay. Whatever it is, as you will see, well, you don't have to memorize any of the stuff. You will just use whatever we give you. Stated here. Okay, if no question, we take a break. You okay? Give me a check if you're okay. Okay, so let's come back at 8 o'clock. I will pause the recording. All right, 8 o'clock. Let's get started. All right, higher order functions. It's what we're going through today for recitation number 3. It comes from lecture 6. Over the years, I find that in all the midterms, which is coming up for us is April, end of March. The most difficult part, it's going to be higher order function, because it's new to, uh, of course, to if you don't have any programming background, even if you have in other languages, higher order functions, it's new because it's so flexible, and so you probably need to spend some time on it. Uh, it can be quite sophisticated with definition. So as I said just now, or I can repeat it here because there should be some new guy here. It was only less than 40 students. Now I have 47. All right. So higher order function means that you are a function in some sense. You also take in other functions and to then work on it and give you the answers. Now, as I show you sum, which is could be a system sum, like here, this is a system sum. As you know, Python allows you to override the name of a function. So the note here is to tell you that you are not supposed to memorize any of this stuff. You are supposed to read the definition and understand what does it do semantically. Okay, syntactically it looks right, usually base cases, and then the recursion. Semantically, you have to know what it does. In this case, it looks like you're applying something to the term A. A is a number, so you're taking a number and give it a term, meaning that you're applying something to the term. So term should be a function, and then you are calling it again with the same thing, and the next A, meaning that you're moving on to the next guy. And this next guy is a function, and it comes from this next function. And from this condition, you know that it's going to end when A, because you keep changing the A. All right, this next A is going to replace the A until the A larger than B, then you're going to stop with return 0, no more recursion. All right, so this is the definition. On the other hand, this sum is simply summing up things. And you can also see this new sum that does it with 3 terms. And this sum t is also 3 terms, it's different 3 terms and so on. So all in all, you don't care what they are. You just care how to read it in the recursive manner usually. All right. Of course, at the end of this exercise, we also ask you to write an iterative version. Okay. And also an iterative version of the 4. All right. So the difficulty is with because these guys take in functions. All right. So these things always involve lambda. All right. Lambda expression or lambda function in a way. So why we use lambda versus the definition? It's that lambda lambda, it's a one-liner. Okay, it means that it's in one line. Like this is one line. Function can be given to a variable. All right, like this one line. All right, I didn't highlight this because this is wrong. Okay, as I mentioned just now, this is wrong syntax. Syntactically, it's wrong already. Uh, cannot have colon. Okay, no colon. Also, you're not supposed to have return. Maybe here I can put a return just to illustrate the point. Cannot have return. Okay. All right. The return is implicitly there. So this is the return. You don't have to say it. It's a one-liner. Okay. So remember that. Now, as I alluded to just now also, You can also have a lambda at the back of the return, or basically you're returning a function in this case. Okay, let's comment out this guy because this guy is error. We run it. Okay, now you can have A. A is a function. If you say A 100 is 10 because 100 comes in here. If 100 greater than 10, yes, so you return 10. Okay. If A negative 100, 100 comes in, negative 100 is greater than 10, no, so you return 0. Okay. So same for C. If it's 100, you return 10. C minus 100, you return a function because this is a function. Okay, why? So we can try. This is going to give me a function. This function is going to add 1 to y. Okay, so if I give him 23, I should get 24. 24. Okay, so lambda function is a one-liner, but this one-liner can be as complicated like here. Okay, all in all this kind of thing, you see that upcoming, they are all working with sequence of numbers. Okay, this is also big data processing, meaning that uh, lots of the data are now stored inside traditionally we call array. Okay, in the context of Python, we call it tuple, we call it list, also set, whatever. Okay, all these are our data structure. It's a collections of things. Okay, in a collections of things, for example, in the World Wide Web, you are actually collection of web pages. Okay, so you're dealing with collection of web pages. So what do we usually do with such kind of collections? There are 5 things we do. Okay, these 5 things you're going to encounter as you go along, and these 5 things actually dictate what you are going to see inside all these kind of questions. It cannot run away. These are the only 5 things that we know. Okay, and this is used over and over again. Okay, what are these 5 things? These 5 things is number one, you do you do searching. You look for things inside this array of things. You do sorting, which are the two lecture, which are lecture in lecture 9, maybe, I believe. Number 3, you do mapping. Number 4, you do aggregation. And number 5, you do filtering. Okay, so what are these? Searching and sorting, you know, in a collection of things, I want to look for number, for example, in here, I want to look for number 15. Okay, number 15 appear here. Okay, uh, that is searching. Sorting means that I want to sort it in order. In this case, it's already sorted as an input. Okay, sorting means sort in sequence. Mapping means that I will take a number, all right, and then I will change it to another number. So 1 become 1, 2 become 3. Why? Because it's a prefix sum. It's 1 plus 2 to give you 3. 3 becomes 6. Why? Because 3 is 1 plus 2 plus 3. So prefix means that you're adding in front. So this is mapping. Okay. Aggregation is just sum up thing. Like here, just now you saw the sum. Okay. Aggregating give you some statistics or find you the median or find you the average or whatever. Filtering means that you take away things that you don't want. All right. So imagine if you are talking about web pages. So you want to sort according to country. Sorry, you want to search according to country. You want to sort according to alphabetical order in the country, or you want to map it to say this page is news, this page is entertainment, this page is sports. These are mapping. Okay, aggregating, you want to sum up the web pages on the number of times that somebody see your page. Right, you're aggregating the total per week or per month or what. Filtering, it means that, okay, I want to, among all the web pages, I don't want those coming from Russia. Okay, it's filtering away those pages from Russia. So whatever it is, it's a considered array, which is a collection of things, and these are the 5 things you always do to them. And all these questions that you were seeing in the midterm, they are all in that flavor. Okay, yeah. So even though it's the most difficult topic, but it's nothing to be scared of. They cannot run away from these 5 items. Okay, so back to our discussion. So this particular function is to do the sum. This particular function is to do some operation, and this operation need not be sum. It can be multiplication, it could be division or whatever. Okay, so let me give you a page. All right, so with respect to this guy, this sum is here. Sum term A next, maybe make it bigger. Okay, all right. So if you have this thing, what does it do? When you go in, you get the term A plus sum, the rest, which is this guy. And term A should be a number now, okay? Because you're applying input a number to a function. And this is a number. This number want to add with someone else. And this someone else is a function, so cannot be added. This guy must be expanded. And when you expand this, it gets into here, which means that the term is now applying to next A. All right, you got an A initially. Now you got the next A, the next element after A. All right. So in this case, if you talk about numbers, it could be from 1 to 2. Okay. In the case of tuple, like some of these guys are doing this tuple from first item to the second item. Okay. So so you get this. This guy cannot be a number, so you expand it out based on the function, this line. You get next A plus sum of this next A now. Okay. The term no change. The next A become next A. Next no change and B. All right. B is the terminating condition for you. So you continue this manner, you will get this term, this term, this term. But one thing you have to remember also is that this term is expanded in this manner, but the sum is from the back, right? Expansion is from A all the way to next A until the next term near to B, all right, the one before B. But the summation is from the back to the front. Having said that, actually, sum itself is associative. So it doesn't matter. You go to the, you want to add it this way or you want to add it from the back, it's going to give you the same answer because addition is associative. Right? On the other hand, when you look at 4, this 4 is not so straightforward now. This 4, it's talking about the same function here, right, which is here. You first you come in this op is like analogous to the term here. This op and this f is like the also like the term somehow. Oh, okay. This op is like the sum here. This f is like the term, right? Because I see that the f is applied to the n, and then the op is the one that combining things. The n is just a number analogous to a and b, okay? But it doesn't need 2 numbers because n itself is keep reducing from n to n minus 1 all the way until n is 0, then it stops. Okay, so the expansion you will see is that op function comma 4 op, it is like folding. You folding from the front all the way to the back. Actually, it's from the back to the front. All right, so the expansion looks from fn to fn minus 1 until f0. Okay, so you have 4 this. It will look something like this until the last guy. But this operator, it's not necessarily an addition, and therefore you cannot assume it's associative. Therefore, you have to respect that if the thing is from the back to the front, you better do from the back to the front, as you will see. All right, so let me just copy this out. All right, it should look like this. Okay, the return result from this until fn, but you first calculate f0, which is the last guy here. Then you take F0, the operator is using this curly A, this curly A to mean the OP. Okay. You must apply F1 to F0, right? Operator F1, F0. You cannot swap the two, right? Because op it's not necessarily associative. Okay, so that you have to remember. And once you get the result, this result again is put at the back of the operator, and then F2 is in front. It's different from rest and F2. Right? We needed to do F2, then the result. Okay. Likewise, result number 2 is from 3 and so on. Okay. So there are differences between sum and fold. Okay. Somehow, because it's an addition, you will just do the addition from the front to the back or back to the front, doesn't matter. But op, you have to respect the thing that it has to be from the back to the front. And op, it's more, in a way, more versatile because it can abstract addition. It can also abstract multiplication, division, or whatever other. Okay. Then also you see that the difference is that this guy has 4 terms, this guy has 3 terms. All right. So whatever it is, let me remind you that you don't have to remember any of this guy because you just have to understand the semantic yourself. Okay. So continuing from what I talked about just now about higher order function or inert function, we now try question one by one. And you will see some of the terms that are used, like forgiveness and so on. Okay, let's try first one, A. Isaac Lam.
Hello.
Hi. Okay, what is your answer for A?
For A, I put 17.
Okay, 17. Let me try. No number? Oh, I didn't print. Okay, 17, you're correct. So let's go through it. X is equal to 2. This X and this X, anything to do with each other?
No, there's
No.
a new assignment.
Okay. This X is this X. These two are the same.
Yeah.
Okay. And they are nothing to do with this guy. And this Y is 5 plus 5. So this is 10 plus 5. So this is what? 15, right? This
Yeah.
is 15. So this is 15. What is this X?
This X takes the earlier X equals to 2.
Okay, that's why you got 17. Okay. Okay, good. Hold on. So let me switch this to below. Oh, too much. Undo. Which is the X is equal to 5. Okay, what will be this guy? What's the answer for here?
Uh, so the Y will now take the X equals to 2.
X
It's
equal to
7
2.
plus 5.
Mhm.
So total would be 15.
15. Okay, this time you're
15.
wrong.
Hmm.
You're wrong. Let's try because there's error. There's error. Cannot access local variable X. Why? Because this X,
Oh,
it's this X, right?
yeah.
So these X that are the same X got nothing to do with outside. So if the two of them are the same, and yet you're trying to use it plus 5, you don't have a value. It is not associated with a value. So
Okay.
this statement is wrong. Okay. So if you do want to use the outside, what can you do? You can do a global. Okay, X. So this time you will work. What will be the answer? This X is what value?
This X should still be 2, right?
Yes, this time is 2 is okay. It has a value now, so Y becomes 7, right? Okay, this X is 5. So this is 5. And so 5 plus 7 give you 12, right?
Yeah.
And then what is this? 12
It'll
plus
be
what?
12 plus 2. 12 plus 2, right?
No, 12 plus,
Or 5, isn't it?
yes, because this X is the global X, which is the same as this guy. So what do you get? 12 plus 5,
Still
7.
17.
Yes, let's try. Okay, 17. One more. Let me just swap these two, right? Okay, like that. You know this is 17, is it?
Yes.
Plus the X, how much is it?
If this one, since it's called before the function, it should still
Mm-hmm.
be 2, right? Because X hasn't been changed to 5 yet.
Oh, that's very good. Okay, so 17 plus 2, 19. Very good. Okay, one more. Let's take this out and take this out. What do you think?
From the, was it the forgiveness? Something, the
Mm,
forgiveness thing, it will refer upwards to 2 this time.
okay, okay. So 2
So
plus 5
Y
give
would
you
be
7.
7. Yeah.
7 plus
Plus 2, we get
2,
9.
9. So this is 9.
Then plus 2x would be 13.
Okay, very good. Okay. All right. So we have exercised our brain on all the items. All right. So this is forgiveness attitude. Okay. So this is 1A. Now moving forward, the rest should be smooth sailing. Let's try number 2. Yeah. Okay. Let's try another guy. Fu Chenyi.
Yes, yes. Hi.
Hi. Okay. What do you get? X is 2.
Uh,
Y is 3.
yeah, so in the
Yeah.
function,
Yeah.
I will take 2 plus 5.
You take
So,
2 plus 5.
yep, so it'll be 7.
Why 2?
Because, sorry. No, because you now define global, right? So you'll return error.
Okay, you're too fast. Look clearly. You are talking about this guy, right?
Uh, oh, you're putting y as an input, is it?
Yes.
So you put 3 as input.
Yes. This is
Yeah, so it's
3.
right, so it's 3 plus 5.
Okay. So
Yeah,
this
so
is
it's
8.
8. Yeah.
Okay. And then
Then 8 plus 7, 15.
8 plus 7, 15. So this is 15.
Plus 3, 18.
18. Okay, let's try. Okay, 18. You're right. Let's see what we can play with this guy. Uh, all right, let's try All right, this should be the attitude for you, huh? So I can try this. Of course, you can try this also yourself, right? Global X, 乘以
Yeah.
Okay, what do I get? Let's try. GY is
So you put in 3 again.
3.
Then that's a good question.
Oh, that's a good question. Yes, of course.
I
All
think it's
question to one.
still 3 plus 5. I think it's 3 plus 5 still.
No, I think it's wrong.
What is it, Prof?
This is you already tell me this is a parameter. How
Yeah,
can you
correct.
tell me this is global? Error.
Uh,
Name X is a parameter and global, so not allowed.
Understand.
Okay.
Yes.
Now let me change this to Y. Is it allowed now?
I think so, because now is X is a parameter, but Y is global.
Okay. So
Uh,
so G what? Y is 3, right? So
yeah,
X is 3.
yeah. So it's 3 plus 5,
3
because
plus 5, 8.
yeah, yeah,
Y is 8.
yeah.
X is 7. So
Yes.
this is
Still 15.
15 plus what?
Uh, you take 8. I think it's 8. 15 plus 8.
Okay. 23.
Yeah.
Okay. Okay, good. So one more. Like this.
So it's 23 plus 3, 26.
Hmm. Okay, good. Uh, all right. Thank you. So
Okay,
let's
thank
try the
you.
next one. Next one. Okay, let's try. Um, there's another Isaac. Isaac Tam.
Hi, Prof.
Hi.
Uh,
Okay, what do we have here?
Uh,
1D.
answer will 1C, you mean? Answer will be 4.
Oh, 1C. I placed wrongly. Answer will be 4.
Yep.
Why? Let's try.
Cause
Full lambda this. So X is a lambda function. And
yep.
a lambda function with the parameter 3. So you get 4. Okay.
Yeah.
Okay. Okay, you get 4. Oh, there's another 4 here. Okay. Nothing else I can. So you have seen the blocking. So this is quite straightforward. The next one here. What about this one? Let's see. Uh, James Tan.
4, then afterwards y is x squared, so 4 squared is 16.
4 squared is 16. 4 is x, so x is 4. Y is a lambda function, so 4 squared 16. What happened to this guy?
Not not related lah. That one is the global parameter, the global variable.
Okay, good. So this is useless stuff. Okay, 16. That's good. All right. Any question? If no, then we move on to question number 2. You okay? Okay. Paste in the chat box and let me see some of your answer. Question 2. Okay. Mm-hmm. Okay, enough. I can see now. Mm. Okay. Oh. Oh. Okay, one of you dash. You wrote it in the lambda way. Oh, and you use the 1, 2, 3, 4. Okay, you are using our sum. Actually, the sum is not defined yet, but anyway, it looks okay. Okay, most of you got it. Okay. All right, let me just paste mine. So question 2. So this is how it looks like. You know that it's again, of course, if you want to check for error, then okay. But we assume that this is n greater or equal to 1 always, so I don't check anything. The tricky thing is mainly on the who is the last term. All right. So when you pass me n, the last term is going to be the one that n times n plus 1. Okay. So the last term is n, but it's a product of two numbers of n and n plus 1. And the sum is such that you 1 times 2, then 2 times 3, then 3 times 4, and so on. So you know that when n is equal to 1, that means there's only one term. You are taking 1 times 2, so your answer is 2. You cannot run. And then otherwise, you return n times that term, the last term, plus one term less. So this is a recursion. Okay, so the answer is 440. Let's run it. Okay, it's 440. Okay. Of course, whenever you have that, by now you should ask, what is the time complexity? Can I see the time complexity and the space complexity? You can type it out in the chat box. What is the time and space complexity? Okay, time is On, space is On. Okay, let's try. Brian Chung.
Hi, Prof.
Brian Chung. Yeah. Why is it On, On?
The space is on because it's a recursive function that calls itself n times.
Oh, it sounds like you're talking all the time.
Oh, sorry, I meant the time, yeah.
Okay, then what about the space?
And then the space it will compute all the functions before adding them up, so it will take n space also.
Okay, it looks like this. All right, so it's you have to stack up all your addition until the end, then you can sum them up from the back to the front. So the time and space are the same. One thing that I should emphasize always, the space can never be larger than the time. Alright. Because if you use that much space, right, for example, your space is already On, okay? Your time cannot be O1 anymore. Your time must be at least On, okay? So that it's the time always larger than or equal to space. Because you need the time to use the space, basically. All right. Okay, correct. On, On. Oh, of course, you can check. Can you do better than that? And can you do better than that? Can anyone do better than that? No, no, no. Can you hear me? Oh, can anyone do better than that? All right, okay, iterative version, yes. All right, I think you are asked to write iterative version, which is question number 4. Let's try question number 3 first. Is the function above a recursive or this one? What is the order of go? Okay, which is what we asked just now, question 3, so we are done. Question 4, if your answer to is a recursive, let me write as an iterative. Can I see your iterative version? Okay, I see some. Okay. Wow. Oh, Junhan, why is it so? It looks complicated. Okay. All right. So the iterative, let's let me just paste it. Question 4. All right. So the sum is 0, and then you want to sum from the range of 1 until n minus 1, n plus 1 is not included. And each time you do it, started with 0, you take the 1 times 2, then 2 times 3, and so on. You return this. And as what I see, Brian Chung, you have the ON, this is the ON time and the O1 space because you only need I, sum, and the range as an object. So that's it. That's your answer. Here's another one. Let me just paste it. Okay, how does this one look like? Oh, this one it's n not equal to 0. Oh, so this one decrement. And the same thing, you started with 0. You started with the last term, which is the n term, multiply with the n plus 1. Then you reduce by 1. So this one seems to mimic the recursion better. All right, so this thing that mimic this guy more. This guy doesn't. Okay. Okay, so this is another version. And again, this is also ON time, but space only 1, O1, because sum is needed. And that's it. No other thing needed here. Okay. Let's see question 5. This is a standard thing in the exam. In the exam, you're supposed to do T1 is what, T2 is what. Okay, T3 is what, T4 is what, T5 is what, T6 is what. You see, everything is lambda. Lambda, lambda. All right. Because one-liner, you can just see this guy check on the length somehow. Okay, so let me see your answer for question 5. Okay. 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 Hmm. Okay, so here's what you have. I write in a different manner. Looks like this. All right, so my sum 2 is this, so it's T1. So now we are going back to the function definition here. Term is to take the value and do something about it. So you want to multiply that number together. And A is the starting, so the starting is a 1. And then the ending is a B, so it's an N. And how to move on to the next guy, it's using increment by 1. Okay, let's try. Check it out whether this is correct. Print my sum to 10, which should give me 440, right? All right, 440. Okay. Now, let me see. Most of you have the same answer. Can I have an alternative answer? All right, well, I'm seeing a lot of them, same as this guy. Could there be another answer? All right, this is the straightforward one. Okay, you got it, I got it. But I'm telling you, there should be another one, possibly. Why? You see this function? You're talking about using 1 to be the n, 2 to be the n to be the n. How about the other way around? You can use 2 to be the 1, 3 to be the 1, and so on. That will give you a different answer. So let's try. That means I want to minus, all right? That means I'm going to use 2, but then I will want to start with 2, and no change to my increment, but my last guy will not be n, but n plus 1. Okay, so let's try. Do I get the same answer? Okay, still the same 440. So this is an alternative answers. So for this kind of test, it's sometimes very difficult to mark because there could be more than one answer. In fact, there are many more answers for this guy. I have another one for you. Okay. Oh, sorry, cannot print there. The print here. Okay, let's see. Why this is also an answer? Let's check it out. Right, we got 440, we got 440. So what this is doing is that k equal to 4 is shifted by 4 positions, and 4 positions shifted, and 1, and this guy multiplied by this guy, and this guy 4 shifted, and this shifted by 4, so it still works. Even 10, it may still work. Oh. Let's try negative number. Will it work? It still work. Okay, so there is no unique answer, but here you see that is a method of shifting things around. All right, so there's number 5. Let's see number 6. Number 6. Okay, can I see your chat? You can paste it on the chat. Okay. All right. Now this fold is kind of easier because it's you're working with addition, so it's associative. All right. What you give me probably you can now know that from here you can see another answer for the fold also. All right. So I see most of you give me this. Let me just cut and paste. All right, give me this. So let me. Let's try. All right. Okay, 440. But you should know now that there will be other answers. You can try. Let's see. No, I don't see any one of you with alternative answers. Okay, here is the alternative answer. It's the same trick. You can shift things around. So instead of x with x plus 1, you can have x plus 1, x plus 2. But then you would have to n at, not n, but n minus 1. Okay. The operator is still the same, x plus y. Okay. And let's see this guy. Okay, we can still call it, it's just override the one. Let's run. Okay, still get 440. Now, here you have to be careful. This is x and this is y. Because this is a plus, so x and y no difference. If the question is changed to instead of a plus, you will do some minus, for example, minus. Then the answer will be different. Okay, let's see the minus. So let's do the minus. We know that these two are the same answer, or maybe we just do the minus. Minus. There should be the same answer, I guess. Okay, 60, 60. Now, if you are not careful, you will change this to y minus x, then the two will be different answer. All right, one will be negative 440, one is 60. All right, because negative subtraction is no longer associative. Okay, so be careful. So that's question number 6. What is number 7? Write an iterative version of sum. Can I see you posting in the chat box? You notice that all your answers, I don't see anyone with a for loop. You are all using while loop. You know why? All right. You see, you just scroll through, you see nobody uses for loop, but all of you use a while loop. Oh, there's one guy with the for loop here, James. For number in index. Okay. So James, can I talk to you?
Yes.
Okay, why do you want to use for loop?
Cause initially I just like I didn't see that it was associative.
Hmm. Okay, so actually yours is more general. It will work for all operations, and you respect the sequence from the back to the front, right? On the other hand, we don't need it for our case because we are dealing with addition only. Okay, good. Actually, this work, and you are using some advanced stuff that not yet covered in our class. You are using a list. You append a list, append item into the list so that you can get them in the correct order. Okay. All right. Otherwise, we should not be using for loop. Okay, let me just give you what I have. Question number 7. All right, here you cannot replace with the for loop. It's not true. Total equal to 0. You are doing it until A is larger than B, and you sum them up. You apply the term to A and add it to the total. Then you return the total. And your A is the next A in each of the looping. Okay. Of course, you can see this as what is the time and space complexity. It is for sure this is a loop from A to B. What is the time and space complexity here? Anyone? Can you type it out? Hmm? Anyone want to try? Or James? James Tan. What do you think the time complexity here?
ON.
Why is it so?
Cause it's dependent on the next function though.
Exactly, there's no n here leh.
Yeah, it's dependent on the next function.
Yes, so you cannot use n. There's no n here. Why in this whole program there's no n? So all of you give me on is wrong. Okay, be careful, This is a trick. There's no n here. It's basically the next function, how fast this A reaches B. So it's the B minus A divided by whatever next is trying to do. Is that okay? All right. Be careful, There's no n. There is no n in this program. We only know that the looping is going to from A, then A plus next A, and next A, and so on. Therefore, this should be the number of loops or looping should be the number of times next function applied to A to reach B. Okay. To reach B or exceeded B. All right. And space is on o1. There's nothing in space. All right, be careful. And next time when you tell me on, what is n, you have to question yourself. If you do that now, so you have to know whether this is correct or not. So we better test it. How do we test it? We will pretend this is what we have, and we call him. We call him, all right, sum iterative, and we print it. See what happened. Print my sum 3a 10. I should get 440 again. Right, I get 440. So I'm confident this is correct with an example that it works. Alright, of course this one can be 10, I think. It doesn't matter. Let's try. Okay. So this is the many solution we can have. Whatever it is, it's still correct. Now, last question. You are supposed to write an iterative version of 4. Go, can I see you try 4? Okay, you can post it. Okay. Okay, this time because you know that the 4 is such that it goes all the way until 0 and then back up to n. If you follow this reasoning, you got it correct. I think James Tan is doing that. Yeah. James is doing exactly what this guy is showing. Okay, let me cut James Tan's and put it there. Oh. Okay, let's try. How do we try whether this is correct or not? So we will use back the same, which is the 4 here. So let's try. Yeah. So let's take this. And then this 4 is this 4 now. Okay. And sum 3, so this is question 8. Let's see whether we get the correct answer. It's a plus. Let's see. Okay, we get 440. Now, Bruce, can I ascertain that my answer is correct with a single example here, like that?
We cannot cause some can be done in any order. There's no difference. However, like subtraction, you must follow the order.
Okay, so now we have to check we don't fail because of association that is available here. So what do we have to do? We go back to our original. Let's find it. Our original is here. Let's take it. And we do it before question 8. All right, so this is our original. Now we do a my sum. Okay. And we intentionally do a division or minus. Okay. So we want to see what answer does this guy give us. So we use it here. And this is full original. Okay. And we want to see what this guy give us. This is not sum anymore, huh? But just call it S. Okay. This is also S. All right. So, and this is negative. So should these two get me the same answer, then I'm more confident that the negation or the subtraction doesn't affect this definition and this definition. Therefore, it's correct. So let's run. I got 60 and 60. All right. Now we have one more test that we can do. That is if we here we can swap these two guys. We take res comma this guy, then we should get the different answer. With that, then we are sure that we get the correct. See, you get 60 but you get -4 from here. So this is the wrong one. So this one should be in this manner. Okay. This is how, from various angles, you try to test out. Of course, testing by example, it's not quite right, huh? But at least the more examples that you work, it give you more confidence that the code is correct. So, okay, is that if you want, you should try divide. A divide, but the division is tricky because the y should not be 0. So let's see whether we get 0. Do we use any 0? Get 0. So to play safe, we +1. Okay, to play safe. Then we will not be divisible by 0. Okay, then both of them, if my new guy, my iterative is correct, this is my original, then the both of them should give me the same answers. Very good. I got 10 and 10. So another last test. We just change this order. You know that. Then see, this is 10 and this is 1 point something. Yeah. Okay, so we can ascertain that we are now very confident that this is correct. Now, with this, we see also that the time complexity. So what is the time complexity? In this case, indeed, you have an n, so you can talk about n. What would that be? Can I see? You want to tell me what is the n? What is the time and space complexity here? Okay, O(n) and yep. Okay, all right. So very good. So we are pretty much done. Then I should encourage you to take a look at some of these more challenging things. You should try them almost every year. This is 2020. This is 2022. I think I have a 2021 also. Almost every year. Yeah, I'm pretty sure every year because we have to have some of these more sophisticated answers, questions. You see, this is lambda, this with this, else this, and so on. higher order function for sure. And then you see this guy and this guy folded to get the result. All right, so this should be quite interesting for you to try out, other than this simple recitation. Okay, I think I'm done with the recitation. Your question. Any question?
Prof, I have a question.
Yes, you are Dash.
I'm Divansh. Yes.
Divash, okay.
So I just want to ask, for higher order functions such as the sum iterative we just did just now, how are we able to determine what the space and time complexity is, or like how can we see the space complexities O1 if we don't even know what the internal functions like term or next are?
I think you are right. Yes. That is a caveat in my answers to you guys. Yes, you are right. We have to. Where was it? Let's see. It's here.
Yes, Prof.
Okay. Yes, you are right. Absolutely. It depends on what terms is doing. If it's doing a lot of funny thing, then the time and space could be worse. So maybe I should correct myself. You only know that the looping is going through this, and so the number of looping should be the number of times next function applied to A to reach B or exceeding B. This number is then multiplied to the time complexity of okay. Yeah, happier now.
So, Prof, I just want to clarify. Is it in that case, unless we know how the function that uses a higher function is implemented, it is impossible to determine what the time or space complexity of a higher function or higher order function is?
Yeah, you're right. Yes, this become another parameters. So this function has this number, a function that generally is just an increment, all right, so that it will stop. Okay, as you see, this is an iteration that it will make it stop. And so this guy shouldn't be a complicated function. It will be a simple constant function. And yes, this term is unpredictable. For example, you can pass in factorial. Okay, then this term will be on. Factorial of A will be OA, all right? And this will be O1 plus O2 plus O3 until OB, or OB minus 1. And therefore, there will be ON squared in total. Right? Or ON times B minus A, which is if A is 1, B is N, then it will be ON times ON. Okay, you're right?
I see. Thank you, Prof.
Welcome. Thank you. You helped me to correct the mistakes. I think what you said is also in here. We will study some of the solutions. I think one of the years it was so difficult. Let me try. Here. Yeah. So this is the most difficult midterm that I saw. But of course, this kind of lengthy discussion or description is not what we would expect you to be able to cover up in the exam. For example, I recall Bruce and some of you actually responded to my forum posting, and I actually said that was in the review. Or not this. All right. I did say that I did give you some more professional answer, but whatever you gave me are good enough because you learn it in that manner. Okay, so some of these tricks, like what I put down here, you need some experience to be able to see them. But now you see it, so maybe something that you can learn. Okay, any other question? Oh, what's the difference between global and non-local? Oh, I'm not so sure. Let's try it out. Let's write a program. Non-local. Will we have it? Here. Okay, so we say global here. Let's see what's our answer. Our answer is 26. So we understood it as this global means 3 here. So this is 3 plus G3. So X is 3. So 3 plus 5 is 8. So Y become 8. X becomes 7. 8 plus 7 is 15. So it's 15 plus original 3 plus 8, 26. Okay. So let's say non-local. So what happened? Oh, it doesn't work. Doesn't work. No binding for non-local Y. Okay, this one I don't know, so I have to check with Google. Global versus non-local Python. The global and local key are used to modify variable scope from function. Oh, enclosing outer function scope, not the global. I see. So it means that you must have another function here, define helper, and y is equal to 10. And non-local, then return helper. This is k plus 5. Okay, let's try this. It's a little bit complicated now. Oh, I should return x plus y. Okay, 31. All right, now this is non-local, you get 31. If I put this global, I would think this global means y equal to 3, not y equal to 10 anymore. Let's try. Okay, you got 46 because they are different. All right, so non-local, it's trying to tell you that it's not within here, but one level up, which is this case, y equal to 10. All right, so there's the difference between global and non-local. Okay. Kailek. Okay. Any other question? All right. It takes a lot of practice for you to be able to whatever exercises you have for now, they are pretty easy in a way that you are dealing with numbers. But as I said before, higher order function need not deal with number. You are dealing with tuple. Okay, you are not just a single number, but tuple or a list and so on. That will require you to then think about how the list or the tuple get passed from function to function. Right, that will be harder. And indeed, some of this is showcasing you how complicated things can be. You can do interleaving. So 1, 2, 3, ABD, ABC can become 1A, 2B, 3C. Is interleaving. And how do you do that? The lambda become this. You take the length divided by 2, and so on. The lambda, the T4 become this. All right, 9:16. Anything else? If not, there are lots of study by yourself needed.
Hi, Prof. I have a question.
Go ahead.
Back to the full question just now. For the space complexity, shouldn't it be OK, where K is the space required to compute next and term?
You mean which one? This one?
Uh,
Question what? 7 or 8? 8.
Question 7, sorry, the sum iter. Wouldn't the space also be OK where whichever is the space bigger required for next or
Yeah.
term?
Yeah, all right. So this space should be O1 is the smallest, so it cannot be smaller than that. So you can safely say it's the space is the space needed for term A. For term. Yeah, you're right. It's like factorial. Always think about it. The recursive version, you will need the space of ON. Yeah, you're right. Thank you.
Thank you, Prof.
Thank you. So now you see that I don't have a playbook. Everything will come to our own analysis, our reasoning, to convince each other. Same for here. This doesn't come from any playbook. It comes from our ability to question what are possible, and we can do it. For example, you give me this M, I can give you transpose of M. Transpose in a matrix sense is that 1, 2, 3, 4, 5, 6, 7, 8, 9 become 1, 4, 7, 2, 5, 8, 3, 6, 9. How do we do that? It's this kind of mapping and so on. It's all by ourselves. And so you are strongly encouraged to question how things can be, or how, if you cannot solve it yourself, never mind. You can once you can create some of these questions, that is 50% to your success. You can then, if you want, you can post it, or you can check with your friends privately, or yeah, or with the TA also. Okay. If nothing, then let's call it a day, and Happy New Year to you. All right, give me a check and then you can go. Bye bye. Thank you. Bye bye. I will shut down now.